automatically, this naming. And when I run this, now we are back in the main program, in the main thread, and it's executing this code that was synchronized. And this code, in my example, just again logs the time and the page length. I don't want to put 200 kilobytes of HTML here. Another possibility is to send a message back. Your background task can always communicate with the main thread via messages. And, well, that's what I was talking before. On the task side, we have this iOmniTask interface, and I can use it. I can use its communication channel to send a message back to the main form. And this message is a simple Windows message. This is declared with the normal Delphi's message declaration, and it takes the value out and shows the value. So I'm timing 2 times here. It takes 0 milliseconds to call parallel.async because it returns immediately. And it takes more than a second to fetch the page, but this was done in the background thread, so nothing is stopped, and we'll get to the page is back. I said there are 3 ways. I have shown 2. That's because both of these approaches, they are good for demo, but they are just hacks. They are not good programming practice. I said async is something that you use for tasks that don't need attention. If you want to return a result, use something that's more suitable for returning a result, and that's a future. Okay? So the future concept, you will find it nicely described in Wikipedia, for example. It's a strange name, but it's a well-defined term which is used in parallel programming. I'm not making this up. So when you use a future, again, you call future on some code. And this code will start and run and run and run, and eventually produce some result. And when you want to access this result in your main program, you call .value on this call returns some interface, and you call .value on that interface. And this call will get the result back, or if the result is not ready yet, it will simply wait. So if you have a simple situation when you say, schedule this, I will do some other processing, and now I need a result, then it's very simple. You call future, it executes to call value, you get your result back. So you call parallel.future. You must tell it which type will be returned from the future, from your code. And that's from this calculation, and then you pass it some calculation. And then at some time, you query this .value function of this future interface. So jumping back to the code, I have here this same HTTP GET, this time implemented with the future construct. So I say parallel.future, returning string, and this is a function that will do the calculation. So this time I used a normal method function returning string, which again calls this HTTP GET, fetches the page into result pseudo variable and returns it back. So parallel.future, type, and function. And I get some interface back. which is iOmniFuture of string, because this is future of string. Then I will do some other processing, nicely simulated with a sleep. And I will query value to get the page contents back. Very simple. So again, I timed two things. One was this basic call. It took 0 milliseconds. And the whole fetch needed more than 1 second. And this code was sleeping only for 1 second. So that means that after the dot value was called, it had to sleep for about 0.3 seconds because before the page was retrieved and everything continued. So sometimes this is enough. You know that you want to schedule some calculation. You know that you have to do some work. And you know that at the end, you will want to get back the result of this calculation. Most of the time, you want to be notified when the calculation has completed its work. One of the ways we've seen before to invoke or message sending. The third option, for example, is specifying a termination handler. So I have this parallel.future as before, future get, and I have a second parameter now, which is parallel.taskConfig, which is configuration block, and this sets a termination handler. And this termination handler is again a normal method. I will put a breakpoint here. So this will be called at that point in time when the calculation completes. So if I do this, I'm in my termination handler. I can check the thread list. So we are really in the main thread. Everything is done. And now, when the calculation is complete, I can call future.value. It will not block because everything is done simple. Everything. OK. While the async has no built-in support for exception handling. So if you have an unhandled exception, if an exception is thrown in your code and your code doesn't handle it anywhere, this exception will get lost. That's just how it is, because there is no well-defined point where you could check this exception. Async is not expecting anything to go back. But in the future example, this is different. If there's an exception in your code, it would be passed back to the caller, to the main form. And when you query the value, you'll get this exception raised. So I have here a demo which will explain this better than me. My HTTP GET call is rigged. If it receives a host name which doesn't exist, it will raise an exception. So let's prove this. Again, I have this termination handler assigned. OK, I still have breakpoint here. So if I call this one now, I will call get. And I got an exception. This is debuggers. That's why I see it. If I call break, we'll see we are still in the background thread. But OK, there's an exception. Calculation has completed. I am now in the termination handler. And I will call .value. And instead of an expected value, I will get this same exception, which was raised in the background thread. So it traveled back to the main form. If I will not handle it here, you'll get the standard Delphi exception reporting window. Just a second. I'm handling it here, so I can convert it to a simple log call. So I see here exception was caught in future.value. Yes, please.
Okay. I saw that the exception is not raised in the original exception point.
Well, exception is raised at original exception point, yes. But nobody was handling it there. There was no try except block. And because of that, it traveled back to the caller. You can, of course, handle your exception in background code, no problem. Just wrap everything in try except and do your exception handling there. But if you forget it, if you forget to do it, the problem with threads is that exceptions in threads are not reported, not even in Delphi. If you cause an exception in tthread, it will go away. You will not know that something was wrong. This way, at least, you get a notification back at a level when you will see it. And you can process it if you want. OK, so that's the future. Next one. Parallel.join. It's similar to async. So you say, please run this code, this code, this code, up to as many as you want. It will create a new thread for each of these tasks. It will run them all. So you can, if you want, run more tasks than you have CPUs or cores in the machine. When you're using parallel.join, it's your responsibility to know how many parallel computations and what you want to start. And optionally, it will wait on all those to complete before this join will return. So you have two versions of parallel.join. One is blocking and waits for all tasks to complete, and the other is non-blocking. It just runs the tasks. You can query it at a later time if they're still running or not, if you want. So I will still stay with my HTTP GET example. I have here a code which calls join to run 3 HTTP GET calls in parallel. So which HTTP GET is not CPU intensive. It depends only on your network. So if you have to retrieve many URLs at the same time, it's quite OK to start multiple fetch operations in parallel. So let's see. I have here a sequential version which does all 3 calls in sequence. It will just block for quite a long time to get all 3. And the parallel version, well, it will also block because I'm using the run and wait. I'll come back to this later. But it executed much faster. It's 2 seconds against 0.9 seconds. Again, join passes exceptions back to the caller. So I have here 2 requests which will fail, first and the third one. And I'm calling this parallel.join, and everything is wrapped back in an exception handler. So this exception from background task will travel back to this join and will be raised and will be caught here, where you expect it to be caught. Debugger will pop up, of course, and once more. And what I got is all inner exceptions one after another. So I have here first exception message, and I have here the second exception message. One belongs to the first task, one belongs to the third task. So if the only thing you want to do is log exceptions in the program, this is enough. Just set up an exception handler, log exception, let's continue, or whatever. But if you want, you can use the fact that this exception is in reality something called e-join exception, which is similar to the inner, what is inner? No, the Delphi has some version of exception which wraps another exception, and you can access the inner exception then. This is similar. I don't remember the name at the moment. So you can catch the exception, and then you can check by yourself which of the tasks failed, what was the exception raised, what was the name of the exception. So in some conditions, you can handle those exceptions. You can respond in your code, but you have to know what was raised and where. So this is possible to do if you want to. So again, so this time I logged more detailed error. There was exception in the first task and exception in the third task. I forgot to add one, but it doesn't matter. And so you have three options, basically. You can ignore exceptions, you can log exceptions, you can process and respond to exceptions, whatever you want. Okay, now to something much more interesting. No, not yet, sorry. Parallel task, as I said, you provide it with only one piece of code, and it will run in parallel on as many cores as there are available. And again, it will optionally wait for those tasks to complete. And this time, I'm not using HTTP GET. I have here something that was actually a question on Stack Overflow, and it turned out it can be nicely solved with the OmniThreadLibrary. So I have a random data generator. The question was how to generate, what was it, 0.5 gigabyte of random data as fast as possible. And the trick here is the bottleneck is not writing to the file, but generating the random data. This is the slower part of the operation. So you can generate data in parallel and then just write everything. I have some sequential random generator here. It uses some very, very random generator. Generates data and writes data out and stops when everything is written, so on. And this thing needs the parallel version. Well, the wrapper is the same, just called general data parallel. Well, this time the code is trickier. Let's see if I put it on my screen. I can put it on the screen. This is now an advanced example. So what I will do, I will start 7, 8, I think, data generators and one data writer. I mean, I will have n tasks generating random numbers, and they will all send their output to one piece of code that will write everything to file. So I'm using T-Omni blocking collection. I remember it. You remember it from before, because it can accept data from all those writers and pass it to one, all those generators, sorry, and pass it to one writer. I will create a counter that counts how much data do I have to write. And again, this counter is something that is part of OmniThreadLibrary and is thread aware. It will work for multiple threads and so on. And then I call parallel.parallelTask.noWait. I will force it to use all CPUs. Again, environment is something that's implemented inside the OmniThreadLibrary and allows you to easily get and set stuff as process priority, thread priority, affinity count, that is on how many CPUs your program is running and so on. So I'm saying here basically run on everything you have. And when you stop, please tell this queue, that it is now complete. So this function will call the complete queue. I was talking about this also before. So what does it do? I have down here, I will scroll later, the writer part, the code that reads data from the queue and writes it into a file. It just says for each buffer which is in this queue, do something, and this something is just write the data out. So this has to be stopped at some time. This for must be somehow stopped, and this is how you stop the for loop. You put the queue into completed state. It will process everything that is in the queue, and then it will stop also. And then you pass some random generator code, which in this case, each task creates its own random generator and says, while I have some work to do, please fill this buffer with random data. This is the same fill buffer as was used before. And insert this buffer into my output queue. So basically, I have here 8 tasks which will loop and put data in the output queue. And my main thread will just read the data from the output queue, copy it to a file, and free this. Well, this data is passed as a memory stream from the background task to here, so it will free this memory stream. And what I have achieved, this is still blocking, of course, but the data is generated in 2 seconds. And if I take a look here, the CPU load was 100%. So I can use all of my machine. And again, if you want to fire those tasks and forget about them, there's a version of parallel task which doesn't wait for everything to complete, which will happily run everything in the background. Yes, please.
If you do that, if you don't wait, how can you get values back?
If you do?
If you don't wait, how do you
Well, if you don't wait, you can still get values back through the iOmni blocking collection. The trick here is, you have to poll it then or something. The no wait option was not really applicable to this case because I wanted to consume the data. If you have a calculation which runs entirely in background, then the no wait option is more appropriate.
Is there something equivalent to the unterminated that you had
Let me check. I think you can do. No, their parallel task is very latest addition to the OmniThreadLibrary, and some stuff is still missing from it. But basically, you should be able to do this. Like before. You can do this to the join, yes, at the moment. and parallel task is implemented by using join. It's just that this simple forwarder is missing in the second, but I will add it. Okay, now really to something much more interesting. The parallel for, it's called for each because for is reserved word, and then you cannot use it directly, and so on and so on. Oh, sorry. So you can use it in the normal way. Lower bound, upper bound, execute some code that accepts integer, and here you do your whatever you do, and this will automatically run in parallel on everything you have, unless you limit it to some course and so on and so on. This is all possible, but I don't have time to go into such details. Or you can pass here some enumerable source. If you have something that implements an enumerator, for example, t-string list, you can put string list here. It will again be evaluated element by element, and in this case, okay, you'll get this my special kind of variant here. Actually, you can say here for each of string, the generics way, and then you will get string here. But that's just a syntactic sugar. In reality, it's the omni value that's passed around, but it will convert it to string just for you. So you don't have to think about it. And this is a complicated beast. Because if some of you were at Marco's talk before, you saw that he solved the parallel for problem with locking. When he needed new value in the background thread, he did